Hi, and welcome back. This is video 2 of 2 for Chapter 12. Now, Chapter 12 introduces us to the concept of statics, specifically through the sum of the torques, the sum of the forces being equal to 0, and also an object being at rest. It also spends a little bit of time talking about what you could ostensibly call material science, meaning, the properties of materials under stress. So that's what this lecture is going to be about. Uh, Mainly the reason why this is being introduced now is to gradually introduce you to the concepts of fluid mechanics and some other stuff that will be talked about later on. Now, that said, um, what I'd like to start off with is a, a short discussion about force, specifically contact forces. For example, if you were to take your finger, we'll say, like maybe here's your pointer finger, and you were to push on something with your finger, the location where you would be pushing, the force that's there or being generated at that point is actually not being generated at a point, but over an area. Okay, so a more realistic way of thinking about forces, specifically, like I said, the contact forces, is that instead of forces being applied through a point, they're being spread out over an area. Now, this isn't entirely true for things like, fundamental forces like gravity. And that's because those are action at a distance forces. And if you actually take a look at the effect of that force over the entire surface of an object or the interior of an object, you discover that it all sort of sums up to being at the center of mass. Now, here, though, many forces that we deal with on a daily basis, basically most of them, are forces that are contact, and as a consequence of being spread out over area, instead of talking directly about force, we'll talk about force over area, which is defined as pressure. Okay. So pressure is typically denoted as P. I'm sorry, I know we've already used P for momentum, but this is just sort of how it is. And it is generally defined as what we'll call the perpendicular force over area. And let me explain to you what that means. So let's pretend that you have a sheet of material, and we're going to exert a force on it. So let's see. Maybe here's my sheet right here. I'm going to disregard thickness for the moment. We're just going to look at the surface. Whoops, that's a weird looking area. Like this. Okay, so if you exert a force against this thing like this, so here's our force. Okay, all of the force in this direction would be distributed over the point of contact or the area of contact. On the other hand, let's pretend you exerted a force like this. Well, if you think about this force here being broken up into pieces, you'd have a piece that's directly into the surface, and then you have a piece that is parallel to the surface. So the part that we're interested in is this part right here, the perpendicular part. It's perpendicular to the plane of the surface. So as a consequence, we call that F perpendicular, or we just let it be known that that's what we're dealing with, and we just call it force over area. Now, the units for force are newtons, we know. The units of area is a length by a length, which is meters squared. And this particular collection of units is also known as a Pascal. Okay, abbreviated PA. And it, like I said, is a more realistic way of dealing with contact forces. Okay, now a good example of pressure, if you want to think of it like that, would be what you experience here, we'll say at sea level, which defines most of Florida almost. Um, and as you stand, say, outside, what's happening is there's a column of air that sits above you that goes all the way out into space, and it has weight, and that weight is pushing down on you. And as a consequence, your body is experiencing the force of that area distributed over your cross sectional area to the direction of the weight. And that's what we think of as pressure at the Earth, at least at sea level. And it's typically called 1 atmosphere of pressure, or 1 atm, which you may have, if you've had chemistry, seen used before. And in terms of pascals, it's about 1.01 times 10 to the fifth pascals. Okay. Now, that said, that's the rough concept, if you want to think of it like that. Um, what I'm really interested in discussing, though, is how these forces cause deformation in materials. Now, that said, I want you to think of the inside of a solid. We'll use solids as an example. And typically, the way we envision these things is you have a whole bunch of atoms or molecules that are separated, by distances, and they're kind of kept in place. Now, they're kept in place by interatomic or intermolecular bonds. Okay, and the forces that connect these things and hold them in their shape, because remember, solids by definition hold their shape, the forces actually look a lot like springs. Okay, so I'm not going to convey all these springs throughout the whole thing, but let's just say it's understood that there are springs there. So imagine having a solid object and you push into it like this. So straight into, we'll say, the surface, which sits like this. So here's the surface right here, like that. Now, if I were to push into it in this direction like this, what I'm doing is I'm compressing. All right, I'm compressing this. And what that does is to cause the average distance between between the atoms and molecules that make this thing up to get less, because I'm compressing it. Now, that's deformation. I'm causing the shape to deform because I'm exerting a force on it. Okay. Now, since different materials are different, they resist, we'll say, compression in different ways. There's a number that you can define that tells you basically how much of a material would be compressed per unit of force. So that's called a modulus. And in general, a modulus is defined as what we call stress over strain. Now, stress is basically what you're doing to the material in an effort to get it to change its shape. Here, since we're looking at a more realistic way of thinking about contact forces, we're talking about force being distributed over an area, or pressure. So here, in this particular case where you're trying to compress something, the stress would be the perpendicular force that I am applying to the area here. Now, the strain is how that object deforms under the stress. Okay. Now, if you were to think of this thing as having a length, like the object overall having a length like this. Oops. We'll call it L naught. Then the act of compressing this thing along its length is going to cause a change in that. It's going to cause a change in length. And the strain is defined as that change in length over the original length. It's unitless, as you can see. So the modulus in this case, that is how well this thing resists compression, is stress over strain, or F perpendicular over the area, stress, over how the length is changed due to that stress. Now, in this case, because this is compressional, and this is also true, if you were to take and pull on this thing and try to get it to expand, that's another type of stress. Okay, that's called tensile stress. So those are both defined by what's called a Young's modulus. Named after Thomas Young, I believe. So the Young's modulus is something that's specific to a material. You can look it up. And it defines basically how well an object resists having itself compressed or pulled on. Okay. Now, so that said, if you rearrange this stuff here on the right-hand side, just to clean it up a little bit, the Young's modulus would be F perpendicular L naught over the area times the change in length. Okay. Now, so again, this is compression or stretching. Now, this is very one-dimensional. You're just exerting a force in this direction and looking at that compression along that direction. But you could define a similar type, not necessarily Young's modulus, but we call it a bulk modulus, over a volume. For example, let's pretend that you had a sphere like this. And actually, let me draw a better sphere than that. That's a little bit better. And let me give this sphere a little bit of depth here. So we understand that we're dealing with a volume. All right. So imagine a sphere like this, and now what we're going to do is we're going to exert a pressure on this thing from all sides, like this, in an effort to compress it. Now, compressionally like this, this thing is gonna withstand this differently than it would withstand just straight in one direction. So this is all, I guess technically you could say this is all kind of in one direction. It's a direction that goes through the center. But if you had a cube or something like that, that may not necessarily be the same. All right, so here, your stress, is the force that's being exerted. Except in this particular case, instead of just thinking about the pressure over area, what we're going to look at is the change in pressure. Because typically what we're doing is we're taking an object from one place and we're putting it somewhere else where it's under pressure on all sides. For example, if you were to stand outside again, you're under pressure due to the atmosphere sitting on you. So you're starting with a pressure. And if you were to, say, swim underwater, you would be experiencing a different pressure. So there would be a change in pressure that you would experience. So again, this would be, not change in pressure, what am I saying? Stress again, F perpendicular over area, which would be a change in pressure like that. That's the best way to look at it. Okay. Now, here, the strain, though, the way this thing is going to deform is going to be through volume. So it's going to experience a change in volume as compared to its original volume. Okay. Now, so if you were to divide these things, you would have your change in pressure over a change in volume over your original volume, or if you sort of clean this up, it's your change in pressure times volume over your original volume. Actually, I take that back. There's your original volume. There's your change in volume. But the thing is that the change in volume that you're going to experience here is going to be negative because your original volume, is what it is. The change in pressure is going to be potentially positive. You go to a higher pressure, so your final pressure is greater than your initial pressure. And in order to balance this out and to make the numbers work, they usually put a minus sign out in front. So the bulk modulus B would look like this. So the minus sign is there just to balance things out. Okay. So this is analogous somewhat to this. So you have the Young's modulus when you compress along one direction or you try to stretch along one direction. And then you have a bulk modulus. When you're trying to compress from all directions like this. Okay, so what we have here is if you think of this right here, if you think of this end as being sort of pinned to the ground or something like that, what you're doing is you're pressing into the ground along this direction of the bonds in this solid. All right. Now, on the other hand, now imagine, and let me see if I can snag this over here. Copy this. I'm going to come over here and paste it. And then what I'm going to do is rotate this. So now it's almost like it's sitting on the ground. All right. Now imagine having that end again is pinned. But now what I'm going to do is I'm going to exert a force this way. Okay, now if you want an analogy to this, it's a pretty good analogy actually, is that if you think of a book, like let's pretend you have a big thick textbook and what you do is you set it on the ground. So we'll say that this side of the textbook is sitting on the ground. Okay, and what I'm going to do is I'm going to say, okay, so here's your spine. Here's the spine of your book right here. Okay, now what we're going to do is we're going to push on the spine of the book like this. And what that does is to cause the spine to deform in the book to look like that. Okay? So this type of strain and stress we call shear. This is what you would associate with cutting. And this is one of the reasons why another name for scissors are shears. Because what they do with a sheet of paper is, if you think of it, you have one edge of a scissor there, you have the other edge here. When you take and you put your sheet of paper in there and you cut, we'll say like this. It's actually bad. That's a bad picture. Why don't we think of it like this? So here's your piece of paper right here. You put one piece above, and there you go, and below like that. When you close your scissors, what happens is at this point right here, you have pushing like this along the edge of the paper, and it cuts it. Okay? So you shear it. Cutting is shearing. Now here, if you think of this as being the area right here, this force now is a parallel force. It's along that direction right there. So it's parallel to the surface. The height of the spine is L naught. And this right here is the change. This is the deformation right there. The bigger the L naught for equal amounts of force, the further this would be pushed over and the bigger the deformation. So your stress here is the parallel force that's being applied against the area, and the strain, the deformation, is that change in x, okay, over the length. So your shear modulus here would be F parallel over A divided by delta x over L naught. And when you rearrange this, it's F parallel L naught over A times delta x. Now, I want you to take a look at what we've done so far. So here, you can press into this, and that's compression, or on the other side, it's strain. Well, not strain, but tensile strength. Here, it's pinned here, and now you're pushing on the edge like that. So those are two unique ways that you can stress a material. Now there is a third way, which I am not going to get into. The physics of it is pretty complicated. The math is pretty complicated. But if you were to think of this as having substance, like this, for example, like think of a cylinder like that. Okay. If I were to take and twist it, whoops, twist it like this with one end pinned, that causes deformation, this circular. It's a rotational deformation. That's called torsion. Now, that is a type of stress. We're not going to get into it. It requires a relatively high level of calculus to address, but it is a unique way that you can stress a material. So, you have three basic ways that you can stress materials. You can compress or stretch them, and there you have a Young's modulus. You also have a bulk modulus if you're dealing with a volume. You can cut or shear them. That's a shear modulus. Okay. The third way is that you can twist. That is a torsion. This is not, like I said, easy to describe. It requires knowledge of tensors and things. Right. So three unique ways that you can actually stress or strain a material. And what's important about this, as we'll discover later on, is that these also represent the three unique ways that you can send a wave through a material. So when we talk about wave motion, we'll be getting into that. In fact, this corresponds to what we will call a longitudinal wave or sound waves. This corresponds to what you would consider to be transverse waves. And these are torsional waves. Okay. So what I'd like to do now is a few examples. So in this one, how much does a column of concrete that's 30 meters long and 1 meter in radius deform under its own weight? The Young's modulus for concrete is 20 gigapascals, and the concrete has a density of 2,400 kilograms per cubic meter. Now, 20 gigapascals may seem like a huge number, but Young's moduli, and in general, most moduli for materials that are normal, have very high moduli in the gigapascal range. Okay, so let's draw us a column. We have a base. Here's the top right here. Let me clean up the base a little bit here. Here are the edges of our column, like this. So there's a picture. Now, it has a height of 30 meters. It has a diameter, or technically, I guess, a radius here of 1 meter. It has a density, and we're going to use the Greek letter rho for density, of 2,400 kilograms per cubic meter. And the Young's modulus for concrete is 20 gigapascals. All right. Now, we want to find how much this thing is going to deform under its own weight. And its weight is going to be defined by how its mass is affected by gravity. The issue that we have here is we don't have the mass, but we can get to it because we know that there's a relationship between density, mass, and volume. Okay, so we're going to use this relationship right here. Mass is density times volume. So the weight of this column on the ground, which is where this thing is being pinned, okay, is m times g, or rho times v times g. Now, what's the volume of this thing? Well, if you think of this as a stack of pennies, we'll say, each penny has an area, and then you're putting each of them to make a column. Now, the area of the cylinder on the base is just the area of the circle, which is pi times r squared. Then you have the height, and this right here is the volume of your cylinder. Okay? So the force here is, and I'm going to use this version right here, is rho times v times g, or rho times a times h, there's your volume, times g. The pressure due to that force is this. Okay? So, our Young's modulus, if you remember, is the perpendicular force over the area times the length over the change in length. We want the change in length. Now, F perpendicular over area is pressure. So that's what we have right there. I'm going to write out the pressure here. And I'm going to note the fact, whoops, not delta L. What am I doing? That's why. And I want to point out the fact that L naught here is just H. Okay, that's all that is. That's just H. So my density, 2,400 kilograms per cubic meter. G is 9.8 meters per second squared. H is 30 meters. And Y is 20 times 10 to the 9th pascals. So if I plug this into a calculator, it's 2,400 times 9.8 times 30, oops, squared. And I got to divide that by 2 times 10 to the 9th, or 20 times 10 to the 9th, rather. I get a deformation of 0.00106. Okay, so even a column of concrete that's 30 meters long, okay, and sitting on its end, it's not going to deform much at all under its own weight. So that ends up being about 1 millimeter. So that's your deformation. Not much at all. Okay. Now let's do another example. So in this case right here, what you're going to do is you're going to take 1 cubic meter of air at sea level, and we're going to take it about 10 meters under the water. Now, the density of water is 1,000 kilograms per cubic meter. And so what's going to happen here is, if you think of this as being the surface of the water right here, all right, at sea level, our pressure initially is going to be strictly due to the air that's sitting above us, which is 1.01 times 10 to the fifth pascals. Okay. Now, when I take that cube of air, we'll just call it a cube, all right, and I move it underwater, it is now under pressure due to the air due to the water that's sitting above it, plus that additional air that's sitting on top. Oops. So now, if you think of this as being, 10 meters underwater, you have the water sitting above it that's pressing down on it, and that's compressing it. And it's compressing it from all sides. Because water is a fluid, it's the pressure is not just here, the pressure's here, the pressure's here, the pressure's all around, which is going to that's going to make more sense to us when we have a good conversation about fluids, which will be later on, like I said. So I'm going to call this distance that this thing is under the water h. That's 10 meters. And the thing is that the pressure that this cube of air is going to experience here is going to be the pressure due to the water plus the pressure of the air sitting above it. So ultimately, when I think about the change in pressure that this thing is undergoing, it's going to be the pressure of the water plus the air minus the pressure of the air. That's my final pressure minus my initial pressure, or just due to the pressure of the water. Okay. Now, so we know the density of our water. The density of our water here is 1,000 kilograms per cubic meter. Okay. We know the volume of our air at sea level. V naught here is 1.00 cubic meters of air. And we also, well, I don't have it here. I'd written it down. I must not have transposed it here. If you look up what the bulk modulus is for air under very specific conditions, it's 142 kilopascals. Now, kilo is just 1,000. Over here, when we were doing this example, we were dealing with gigapascals, which is 10 to the ninth. So one question you might have is why the difference between the two? Why is this so much smaller? And that's because air is very compressible. It doesn't resist having itself compressed very much. Okay, and the way it resists is actually nonlinear. So this is a good approximation of this problem, but in general, the way you would deal with the compressibility of air is a little differently. But we're going to run with this. So this right here is 1.42 times 10 to the fifth pascals from a compressibility standpoint. Okay. Now, so this is going to work the same way, basically. You could think of a cube of air here that has a column of water sitting above it, okay? And that column of water is going to have a volume of H times the area that it's sitting on, which would just be the area of the top of the cube, okay? So the mass of the water that's sitting above us is just like before, its density times its volume, okay? Or density times the height of that column times the area that's sitting there. Which means, if you think about it from that standpoint, the pressure of the water is mg over the area, or once again, rho gh. Okay? So our bulk modulus is going to be, let me go here. Actually, we just go over here and take a look. minus delta P V naught or over delta V. And this is what we're trying to find right here. So delta V is going to equal to minus delta P V naught over B. Delta P we've already found. That's P sub W, which is this right here. Rho GH V naught on the top with a bulk modulus right here. That's 1,000 kilograms per cubic meter. That's 9.8 meters per second squared. That's 10.0 meters. 1 cubic meter divided by 1.42 times 10 to the 5th pascals. So if I do this, I get 0.69 cubic meters is the change. Now, if you think about that, if you think of change as final minus initial, then that means that, oh, negative, by the way, that means that your new volume is going to be 1 cubic meter minus 0.69 cubic meters. Which is actually ends up being about this. So this thing's compressed quite a bit. And this, incidentally, is the reason why if you swim to the bottom of a swimming pool and you haven't cleared your ears, you can feel your ears hurt. Okay, and that's because as you go underwater, the air that's inside your ears actually is compressed due to the pressure on the outside. And as a consequence, it squeezes the inside of your ear. It causes it to hurt. The same thing can happen to your sinuses, and it can also happen to your teeth if you have a dry socket. This is one thing that divers deal with all the time. This is the same thing, in reverse at least, that causes the bends when you dive. When you're below the ocean, deep, we'll say, deep being below about 20 to 30 feet, and you spend a lot of time breathing air in, you're also breathing in nitrogen, and your body saturates your tissues with the nitrogen that you breathe in. It's used throughout your body for all sorts of metabolic processes. So you have these little bubbles of hydrogen, or not hydrogen rather, but nitrogen that are sitting, inside your tissue. And if you go up too quickly, what happens is they expand in a reverse process and they do tissue damage. And the reason why they call it the bends is because some of that tissue is neurological. And people have a tendency to seize and do things like that when they get up there, so they call it the bends. So the solution is to very gradually go up when you dive and take what are called deco stops at safe places for, anywhere from 5 to 10 minutes, possibly 20, depending upon how deep you've gone, and, even more depending upon the situation. And as a consequence, what that does is to let your body process out a lot of the nitrogen that you breathed in. And the slow ascent means that you don't have this rapid tissue damage that's done. It still does damage, though, and it'll wear you out if you ever dove. Anyway, so as an last example, what I want to do is I want to look at the effect of shear. So how much force is required to punch a hole through a sheet of copper that's 1/4 of a centimeter thick? The hole has a diameter of 2.56 centimeters, and the shear modulus for copper is 44.7 gigapascals. Again, as you can see, this is huge. So what we have here is a disc of material that we want to sort of punch out here, and let me just. take and clean this up a little bit to make our disc. This is what to punch out. Like that. And it's, obviously sitting pre-punch as the sheet, which I'll sort of show like this. Here's the edges of the sheet leading into it. And the sheet surrounds it, obviously, all the way around, too. But the reason why I'm doing this is to show you that this right here, if you think of these as being the pinned areas, your force is like this. So as you can see, your force is going to be parallel to the area being the area of this all the way around that you're trying to punch. That's your area. Okay. Now, the deformation, this is your length. This is L naught. Okay, so this is L naught. This is what you're pressing along. And this right here is the deformation right there, delta x. So your area is along the edge of this disc right there. And here's your force. So if you remember what your shear modulus looks like, it's F parallel over area times the change in x over L naught. Now here, we know what our shear modulus is. Our shear modulus is 44.7 times 10 to the 9th pascals. And we also know delta x. This is how much we need to deform. We need to punch through it. So we're shearing it this much. It's a quarter of a centimeter, or 0.0025 meters. Now, we're given a diameter. The diameter here is 2.56 centimeters. That would be L naught. But what I'd like to point out is that our L naught is 2 times the radius. We're going to use that to our advantage here. Okay. Now, the area that we're looking at here is the circumference of the circle times the depth. So our area here is 2 pi r times delta x, or you can think of it as pi times the diameter times delta x, or again pi times L naught times delta x. So here we're looking for the force. So if we write our shear here as F parallel, which is the force, over the area here is, I'm just going to write as, we'll say pi times r squared. Actually, that's not the area. What am I thinking of? The area is what we just got. Pi L naught times delta x, rather. Sorry about that. Times, we have delta x over L naught. L naught is d. Okay. Really, all we're solving for at this point is F parallel. Yeah, this is d, remember? All right, so our shear here is 44.7 times 10 to the 9th pascals. D is 2.56 centimeters, or 0.00256 meters. Gotta square that. Then we have a pi. So let's see here. 44.7 times 10 to the ninth times 0.00256 times pi. So I get that this is going to take 9.2 times 10 to the 3, 4, 5, 10 to the 5th newtons. This is how much force is going to take to press through. All right. So as you can see, the shear stuff's a pretty big deal. The compressional stress is a pretty big deal. Like I said, I'd love to talk about torsion, but we don't have the ability to do it. That said, we're going to revisit this again later on when we talk about fluids and stuff. And that is it for this chapter.